I'm going to talk about cool technology that we've been developing at Motion DSP for the last 4 years. It's about multi-frame video enhancement, and I'll be presenting, as I said, with Nemanja Grujic. I'm a VP of Engineering. I first want to say I'm so excited to be here. I've already had a great day met with a couple of groups here doing a very exciting work. Thanks, Sanjay, for putting this together. And we met through a common connection at NVIDIA. And I'm glad to see that a lot of people here are involved with what seems to be a really state-of-the-art and leading-edge research on some very practical things that are out there in the real life. This is a brief outline of my talk. I'm going to start with some brief history of video coding and basically get us to the point where we are now, where we believe there is a paradigm shift from the era of video coding to the era of really video processing and beyond. We have a couple of shipping applications, one for the forensic space, the other one for consumers. The other one just launched last week. It's called vReveal. I encourage you to go to vrreveal.com and download the trial version or get it from NVIDIA's site. I hope by the end of the hour to demo at least one of those. I'm going to talk about performance, which is really critical. And this seems to be one of the first applications that's bringing visual computing to the masses. And then I hope to have Nemanja joining from NIST to talk about a couple of things we've learned about GPU programming and hopefully get some ideas about where we can go in the future. So Motion DSP has been around for about 4 years. It started as an extension of research done by Professor Peyman Milanfar at UC Santa Cruz. And what we do, we make video enhancement software. And what video enhancement is, the definition has been changing. It used to be that it's whatever you like your a picture to look like. So I still remember when I was a kid, we had a TV like this, and basically we had the contrast, saturation, brightness sliders. But it turns out that right now you go and get any of video editing software, Premiere Pro or Final Cut Pro, Sony Vegas. It's still surprising to see pretty much the same subjective enhancement you can do to video. You can do a lot of great nonlinear editing, but there is nothing really from the mathematical side that deals with the problem of video reconstruction. And we believe that there is a void there, and there is a huge need for something in this space. So we built software that hopefully will make video better in the objective way. And for lucky, we'll see demo in about 20 minutes. But what I want to show now are some examples. So these are pre-rendered examples of what video looks like before and after it runs through our software, and I'm going to show a variety of clips here. This one is from your regular digital camera, shooting video, shooting in video mode. This example shows that not only you can get better clarity of video, but also do a lot with stabilization. Here is another stabilization example. This is another example from a consumer side. So I'll show both consumer and forensic examples. And now this doesn't give it a real justice because it's on a projector in a pretty lit, well-lit room. But again, I invite you to get the software and take a look for yourself on a computer. This was a real video. It was very dark, and what one can do by first bringing levels up, and I mean, everyone can do another contrast, but that's going to bring all the noise out because you're not doing anything with PSNR. Now, if you apply this filtering across many frames, and multi-frame technology is what we do, then you can still get something useful out of it. This is another example of improving resolution, color, and stabilizing video. This is a clip from what we believe is our kind of target audience for a consumer side of a business. And this is an interlaced video from the UAV. And we work with, so let me just see, just play this one again. So you can see basically the difference that our software can make to someone operating this. These are more clips from cell phones. This is again the similar clip where we can identify just a region of interest and apply our processing. More shaky clips and more interlaced clips. This is another interesting resolution enhancement clip where you can see that we can bring the details back from something that's not very legible to here. Okay, I think this can get you an idea about what our software can do. But to quickly revisit what's been going on with digital video over the last 20 years, obviously, our communication is becoming increasingly visible. We use digital video on a daily basis. A very short history of digital video from about mid-'80s with introduction of D1, and for consumers, QuickTime a little bit later. Pretty much until now, it's been all about encoding. We believe that right now we are entering this second stage of digital video processing that really has its foundation in wide audience. And that's really enhancement and characterization of video, with focus shifting to post-processing. And stage 3 is obviously a holy grail of understanding what a video is and dealing with things like video search or human-computer interaction. So stage 1, I don't think anyone needs convincing how much we are surrounded with digital video, from TV to movies, from video on the go to video conferencing. Digital video is all over the place. And the main focus of digital video of this first phase was how do we get video from point A to point B, where point A might be here and point B might be the other side of the world, but also might be on the local hard drive. So it turns out everything is about encoding, and encoding is a well-defined problem because you have a source, it's right there, that's your original. You want to pose a problem in such a way that you encode and then decode on the other side and come as close with certain constraints in terms of bit budget that you have to the original. And this problem of video encoding is more or less solved. Maybe some people from research side won't agree with it, but industry voted, and the solution is Advanced Video Coder, or H.264. There are not even plans within MPEG committee to right now go any further. So how H.264 works? It's so-called hybrid coder that combines temporal prediction with spatial transform coding. Spatial transform coding is more or less, JPEG or something else DCT based. It's not very interesting. But what's interesting to see in the structure of a standard hybrid encoder is that basically, as new frames come in, they're predicted from previous frames or previously encoded and decoded frames to get rid of a drift. And what we end up with are motion vectors that are defining prediction, and texture, which is basically prediction error. And although having better motion will improve quality and performance of encoding, pretty much any motion will do the job. One can have inaccurate motion as long as you're willing to put enough bits in the texture. You'll still get a result. Now, your PSNR for a given bit budget won't be perfect, but it's going to work. Now, conclusion is that motion indeed doesn't have to be perfect, which doesn't mean that H.264 doesn't have a very good motion model, and it's a product of almost 20 years of research in that area. And in a nutshell, it's ray distortion optimized variable size block matching with quantized to a quarter pixel motion vectors. And it works great in the context of encoding. The reason why it's quantized and why it's block matching is because the rate of motion is also important in the overall bit budget of the encoded bit stream. And it turns out that quantized motion can be compressed very efficiently. Now, let's see how things looked like 10 years ago, and how did they look now in the world of digital video. Only 10 years ago, we had only a handful of creators. There were studios or DVDs were made in the big Hollywood, powerful compute centers where encoding would happen, and our decoders were very incapable. Basically, as recently as 2000, 2001, you couldn't even decode MPEG-2 on a PC. You would have to get a separate hardware card just to watch DVDs on your PC. And now, it's a breeze. And then most of the content, most of the digital content from 10 years ago was high quality. Those were, Hollywood movies or, content from studios. What we have now is a shift of paradigms. Now we have millions of people taking digital video all the time. We have many low-power encoders. Now we have very powerful decoders or post-processors. And a prime example is a GPU. And a lot of content that we dealing with now is of a low quality. So what we see as a new paradigm is this video world after we take encoding problem as something that's solved. And certainly better encoding can help, but it's often limited in what it can do, because there are problems of small aperture, which means that not enough light gets on a sensor. These sensors in many devices like phone cameras and digital cameras are pretty cheap. DSPs are cheap. So sometimes you can't implement the most efficient coding. Battery life and power is limited. You are constrained in terms of how much you can send in your uplink. Let's say you're streaming from your phone, for example. What's probably the most interesting thing is that nobody has a Hollywood film crew with him all the time. So even if you have like an HD camera, you shoot indoors. There's a really good chance that your video is going to be noisy, and you won't be very happy with the result, and it won't look like a Hollywood movie. So, shifting the problem from the encoding to post-processing, there are a couple of things we can do once the video is there, once it's recorded. And one is to say, well, I don't want to do this. I'm just going to despair, and I'm just going to wait for better hardware to come in 5 or 10 years. The other one is, if I shot something, I said, oh, only if I had a better camera with me, so let's do it again. So even if you're on a birthday party, that may work, but sometimes you're going to have video where there's a robbery, or there's something going on. That's all you have. So you can't have a do-over. Or C is, hey, let's just deal with what we have in a smart way. And fortunately, video has this unique property that's different from audio and from stills, that you have multiple observations of the same thing, and you can have dozens or hundreds of those. Because with still photo, sure, you can do a better interpolation, smarter interpolation. You can fix contrast and do deblurring, but you have that one instance. That's one observation. With video, shooting at 30 frames per second, shooting at 30 frames a second, it's sufficient for you to have something in the scene for 10 seconds, and you already have 300 observations of that thing. And that really helps us do a lot with video. And some of the things that we can do are fixing resolution. As I said, we can do a very sophisticated noise removal. And we can do lots of things on the stabilization side, get rid of camera shake. And that's what our software deals with. Now, I get this question all the time, and we just launched a new product, and there are people on forums online and on reviews, and they say, well, this is impossible. It's, you put something in, how you can make something out of nothing. And it's true that we are not adding new information to the video as a whole, right? I mean, that information is right there. We're not using anything that's external. But multi-frame processing can increase information in each individual frame. And this is what I'm going to illustrate now. Every video, and I think this one should play it, it's like a very low resolution. Right. So this is a real example. This is not made up example. This is cell phone taking video off of a bookshelf. And that video consists of many frames. Now, if I take just one of these frames and blow it up, it looks like this. And I'm just going to blow one detail over here. So you can try to read what's out there, but maybe this looks like dynamics. Maybe if you saw these books before, maybe you know what these are. But it's not great. Now, what we can do is bring information, and I'm going to talk about it a little bit later, what we exactly do, but bring more information from neighboring frames. And we can go from this to this. So it's not much. We just brought 2 new frames in. So this is with 1 frame. But look, the one on the right. So this is with 1. This is with 3. OK? So now we're going to bring 1, 2, 3 more. And then we go from this to this. So it's a little bit better again. And we're going to bring more frames in, and it's going to become even more better, even better. And finally, we can do, this was purely temporal processing, and we can do some things that are used in spatial processing and end up with this result. And just to make the difference now to point to a difference between the original and the final version. So this was before, and this was after. OK. So to get back to the question, does it really work? It does. It really works. And entropy of each individual frame can be increased. And that's what we perceive as video that's more legible or better looking. And that's what we do. Now, the reason why I brought up a motion that was used for video encoding is because a lot of people still have their mindset locked into motion for video encoding framework. And they would ask us, well, why can't you just simply reuse this fancy motion estimation from H.264 that many people before you developed? And the simple reason why that motion can be used is that the structure and the structure of a problem is totally different. As opposed to kind of closed loop where we could always have this prediction error to help us correct inaccuracy of motion. Here we have an open loop problem, which means we are past. Input frames are here. We've encoded them. We've decoded the frames. And now we're stuck with low resolution output frames. Now here with, let's say, 5-tab filter, I want to get a high resolution result here from 5 decoded frames. If I don't have motion that's completely accurate, that's like float point accurate, there is nothing that can help me to fix it. So that's the reason why, because there is no ground truth motion available, we can't work with quantized motion. So everything has to be float. You can't work with, half pixel, quarter pixel, 8 pixel, 1/8 of a pixel, 1/16 of a pixel. You simply can't do that. And also, you can't use block-based motion. Just because your true motion in real life doesn't align with blocks. Now, one benefit there is that obviously our amount of motion that we're going to generate is going to be huge. But fortunately, we don't have to transmit that anywhere. And that's the restriction that motion used for encoding had. So, to recap, in video coding, motion's usually from frame to frame. Here we have many frames, so we have to look at motion correspondences through many frames. Instead of block matching, we want to use true motion. Instead of quantized motion vectors, we want to use floating point accuracy motion vectors. And finally, instead of simple temporal model, we want to have advanced temporal motion model that will tell us that, for example, one trajectory should be used for the entire length of a buffer, and the other one, because of occlusion, should be used only over a number of frames where the object is visible. Because you can have a situation where objects are getting occluded or leaving the scene. So around this concept, we've built what we believe that in commercial world is the first start-to-end multi-frame, where multi-frame goes from 5 to 50, depending on our product. And we built this video enhancement framework, and we ported it to GPU completely. So you can take advantage of a GPU. And I'm going to show some performance benchmarks later on. So moving on to applications, as I mentioned, we have 2 products that are shipping now. One for forensic intelligence community. We named that one Ikena, and that's the software for chasing bad guys and recovering license plates or faces in the dark and fixing aerial imagery. That software has I don't know if I'll be able to demo. Has many options, but it's still very easy to use. Practically, an operator can get started in 15 to 20 minutes. It's a big part of what we've done is to automate a lot of this. So, and even bigger efforts to automate everything went to our consumer product that just launched last week. It's called vReveal. I believe that we brought the first one-click fix to video, but one-click fix in a, if you want, like mathematically accurate way, where it's not just tweaking with color and contrast, but doing something more with video on the post-processing side. They both rely on our patenting technology. We have a number of patents that are coming both from UC Santa Cruz, and that some of those developed internally in the company. So Ikena, that's our software for forensic applications. Right now, all our software is Windows only. We do have a version of a server-side product that's working on Linux. No Mac support yet. It is basically when people ask us to describe it really briefly. It's what you see on CSI, except for it's for real, and sometimes it's going to get you spectacular results, and sometimes it's just going to get you whatever is there. So it's not a magic wand. You won't get great results all the time, but it does a pretty good job of helping growing base of customers that are using it around the world, both in the government, in the private sector, law enforcement, intelligence agencies, and we're happy to work with them. We have a GPU accelerated version that's running on NVIDIA's CUDA. vReveal, as I said, just launched. It's the same core engine now with options and interface that's matching consumer needs. Obviously, you can't generate the same forensic result from it, and it honestly wouldn't make business sense for us to have that. But it can run, again, on any Windows machine. It's CUDA accelerated, but again, if you have only integrated graphic card, it's going to work. So it works on a CPU only. If you have ATI card, it's going to work. It's just like will also run on a CPU. And if you have old NVIDIA card, it won't use it. But if you have G80 or later NVIDIA card, then it's going to make use of it. And it just launched last week. I encourage you to go to vReveal.com, download, and try it. It cost $50 after a 30-day free trial. So let's look at some performance benchmarks. This is one slide that we made for the launch of vReveal, where we wanted to show how a set of GPUs compares with a set of CPUs with some numbers attached, how much these cost. So these are frames per second performances on a Vista system for fixing in real time VGA signal. So you have 640 by 480 signal. So how fast we can decode, process, and encode that signal. And starting from dual core, that's at about a couple of frames per second, maybe 3 or 4. It goes up to 7 and then 9 on what's pretty much state-of-the-art CPU, Nehalem i7 core. And on NVIDIA graphic cards, even on a low-end card, we get performance that's matching much more expensive CPU. And then we go all the way up to 25 frames per second on the top-of-the-line NVIDIA card. So we roughly get 1 to 3 speed up between comparable GPU and a CPU. This is similar example with more data points, and then for a couple of different resolutions. This is for QSIF. That's your typical mobile phone video, or few mobile phones are even shooting that. That's 176 by 144. QVGA is 320 by 240, and then these two are being upscaled by a factor of 2 and processed by using 7 matching frames. So that's like looking at a current frame, 2 before, 2 after. I'm sorry, 3 before and 3 after. And running entire suite. I mean, in addition to our multi-frame temporal filtering, we also do color correction, contrast correction, then stabilization, which is a natural byproduct of motion estimation that we do. So all of that with decoding and with encoding is taken into account, and we can get for QVGA a little bit over 30, and for VGA a little bit under 30 frames per second in saving things to disk. So it follows fairly smoothly the curve of increasing number of cores on a GPU, increasing clock of a GPU, and same thing with number of cores and clocks on a CPU. Sure.
Are you going to talk a little bit more about the computational structure? So I'm actually intrigued that you only get a factor of 3x, at least from
Right. Well, there's some fixed cost involved. Decoding and encoding happens on a CPU. So that's fixed cost for both CPU and GPU pipeline. And then in the current model, data is decoded on a CPU, raw frames are sent to GPU, entire processing happens on a GPU, but then resulting frames are brought, right now in an existing architecture, brought back to CPU and then sent back to driver, to display. So there are some overhead. There is an overhead. Now, theoretically, we believe that we can go to probably closer to, and NVIDIA just released a new CUDA where some of that memory up and memory downtime could be saved. We still have more ways to go in terms of efficient implementation, but right now we are at 1 to 3. We believe to get to maybe 1 to 5, 1 to 6. But for now, there are a couple of uses of the software. One is you can preview your video in real time. That means you never have to really save it to the disk, and then performance is higher. That means it's your real-time playback post-processing filter. You just play something, it's running on your GPU, your CPU is more or less idle, and you can do other stuff if you want, and you can just watch it, you don't even have to save it. So for that application, all you need is 30 frames a second, right? For save to disk and for going to larger frames, sure, we would like to go and improve performance. We're also working on multi-GPU configurations and on improving not only optimization, but improving the algorithm and see where we can save more time. But right now it's 1 to 3.
So for the part that you do accelerate on the GPU,
Mm-hmm.
do you have numbers for how much that was sped up?
I don't have it here in slides, but definitely I have those numbers. Now, that depends heavily on the filter. Some of the filters, and you know what? I'm going to fire up the software on my computer anyway, so you'll see what the filters are, and I can tell you which filter gets the most. So some filters will parallelize better than others. But then also some filters will spend more time than others, so the difference there makes the bigger difference overall. So another thing, so all these numbers are for Vista. And I know that lots of you are doing CUDA development here, and I just wanted to bring this one thing out because numbers look much different. So the difference from previous graph is I just add the last bar here, and that's GTX 280 on XP. And you can see that Vista versus XP performance is 20 to 30% slower. And the reason is Windows Display Driver model, right? Because it's partial implemented in user mode, and every API call has to go and has a fixed overhead, as opposed to XP that goes directly to the kernel. So numbers do look better. Now, CPU numbers are the same, Vista. So right here, it's like 1 to 4. And maybe I can see here. i7 was about 8, and this is definitely over 32. So that's right there fixed, 20-25% performance hit. And oh, I'm back online, so it's right in time because it's time for Nemanja to take over. So let's call him. Need help from friend. That's my lifeline. Hello, Nemanja? Hello, Nemanja?
I hear him vaguely.
Yep. So we'll bring him up.
Will you get the volume up on the code? We're pushing our technology to the limit.
Hey, Nemanja, you there? Okay, so he hears me now. We.
Ask him this.
No. Okay, so let's call him on a cell phone. Let's just find it.
Expensive. It's $0.25 a minute.
Okay, so he tells me to call just a different phone. Third time is a charm.
Hello? Hello?
Oh, hey, finally. So, Nemanja, you
Yeah.
hear me?
Yes, I hear you very well.
Excellent. Okay, so this was just in time. I don't know if you had the chance to follow the webcast online or not, but we're now at a segment where you kick in, and Nemanja is our chief GPU engineer. He graduated from University of Niš in Serbia, and then spent a couple of years in Berlin at Technical University in Berlin. And he's going to talk about a couple of lessons we've learned from working on CUDA development for the last year or so. So Nemanja, take over.
Hello. So apparently it's my part now. So I'm Nemanja Grujic from Motion DSP, and I will talk to you about a couple practical examples from practice we encountered here by developing our application. So let's go to the first example. Our problem is next. So we have complex real-world application which is run in a multi-threaded environment. Our algorithms, our filters are added and removed dynamically, and we have multiple executions of same algorithm with different parameters during the run of the application. So the parameters are the video size, frame rate, and so on. So the practical problem with GPU programming which arises is memory allocation and allocation. Nicola, next slide. Okay, the fact is that memory allocation in CUDA on GPU is really expensive. So we got that we have over 10 milliseconds of memory allocation per frame if we allocate all of our temporary variables in each frame. So our first obvious solution was to allocate temporary buffers in advance. This was not so good solution because we have large memory consumption, because each filter in our video processing application allocated its own memory. So the overall memory consumption was the sum of memory required for each filter. And also the code was complex and error prone, since everything was run in multi-threaded environment, and you needed to reallocate all the buffers when video size changes, etc. So we noticed that we were allocating same memory sizes all over again, because many temporary buffers for needed in video processing are the same, equal to the size of the video frame. Plus, our execution is periodical since we are executing almost the same code for each frame. So the obvious next step is to build simple memory manager, which is practically a singleton for managing CUDA memory. This singleton helps us to reuse the same pointers for different applications, so in different among different filters, So next slide. Okay, this memory manager is encapsulating actually a hash table of memory pointers, memory record smart pointers. Okay, each of these pointer encapsulates pointer on GPU memory, the size allocated, thread ID. So the thread ID is needed because CUDA has different memory space for each host thread, and each memory record keeps track of the age. So the memory record can be deallocated, really released, when its age goes old. The operations which this simple memory manager provides is memory allocation, memory free, and tick. So the tick I will explain a bit later. Next slide. Okay, memory allocation. So memory allocation is very simple. We are looking in our hash table, and we are looking for the required size and required thread ID. So if pointer with similar size, or a bit same or a bit larger size, and the same thread ID is already allocated, we are just returning it. So it's very fast. We do not call allocation on GPU. If we don't have that kind of pointer already allocated, we allocate it and return it. Memory free just returns the memory record to the hash table, so it can be reused by whenever is needed again. The tick operation is very interesting. We are something like taxing this memory manager. So this tick operation, it increments all the age of all free memory records. So if it checks if some memory record goes old and permanently releases it, so the memory won't, so we don't have memory leak. We are in our case ticking after processing every frame. Next slide. Okay, the last point about this memory manager, we've implemented this smart pointer. So it is just a template class which overrides the cast operator and uses the memory manager. So if you want to get some memory on GPU, you just declare the variable, let's say PTR in this example, with wanted size. Here is height times height, and the smart pointer uses memory manager to get required pointer on GPU. So you use the smart pointer, this PTR, just as you would use float pointer on float, and it's just that. So nothing more. At the end of the code block, the destructor is called automatically, and the pointer is released and got back to the memory manager. So that is how we solved this allocation problem. Next slide. Okay, conclusion. So by writing this small and very simple memory manager, we got faster execution. Actually, we removed around 10 milliseconds per each frame, which is a significant amount of time since we are going for real-time performance. So we have around 30 to 40 milliseconds per frame. So 10 milliseconds is around 25 to 30%. So it is significant time. Okay, but by doing this small memory manager, we also have a smaller memory footprint. Now the memory consumption is approximately the max. So if some filter, each filter allocates some amount of memory, and maximum allocated memory is now our is now the memory we are using. So, and the final benefit is that we have much simpler code. So our smart pointer is really extremely easy to use, and the code is now smaller. Okay, that is the end of this first example. Now I will go to the second example. Next slide. Okay. Next example requires a bit of CUDA knowledge. So it addresses the problem of convolution. So since we're doing the video processing, the convolution is really heavily used. So it takes significant part of the execution time. We are, in some average case, calling 50 convolutions per frame, up to 70 convolutions per frame, Gaussian convolutions. So at some point of time, these convolutions use around 60% of all processing time. So previously we used this separable convolution example from CUDA SDK, but we've seen that we must optimize more since that was the 60% of processing time. So next slide. So the first step in our optimization, little optimization scheme, was to use very simple CUDA kernel for 3x3 convolution. Actually, two kernels for row convolution and column convolution. So I have this a little code snippet from CUDA kernel. It accesses just the actual pixel, current pixel, the previous pixel, and the next pixel in the row, calculates weighted average, and writes it in the destination. So it's really simple. And the next step in our scheme is to combine this simple kernel to write convolution for general size. So as you probably know, when you apply two Gaussian convolutions in a row, so one convolution and other convolution, you again get Gaussian. So this property of Gaussian we are using to make a decomposition of larger Gaussians, and to run it using our simple kernels for 3x3 convolution and 5x5 convolution, which I didn't write here. So yeah, you have here the formula for the approximation, and you can look at it after presentation in the slides. So next slide. Okay, when we've done this, we've seen that our new scheme, like the composition of larger convolutions to smaller convolutions, we've got some speed improvements, but it was not much faster than our convolution separable example from CUDA SDK. So we've noticed that row convolution works much slower than column convolution. After analyzing the code, we figured out that that is because misaligned float memory access in row convolution, and column convolution does not suffer from that misaligned memory access. So we actually figured out to use only column convolution. So if you're using column convolution and then you transpose your matrix, then you again use column convolution and transpose matrix. You get the original matrix which was convoluted. So next slide. Okay, I must make a notice that this column convolution and transpose is written in the same CUDA kernel. At first we used this naive transpose scheme to just map the pixel xy pixels to yx pixel, and that worked very bad. They didn't use the CUDA shared memory. After that, we wrote a little bit smarter transpose, which transposed each CUDA block in the shared memory, and then written it in the global memory. Now that is the final optimization. So our convolution works in average 60% faster than convolution separable example. And next slide. Okay, here you have all the code for our convolution column and transpose, one CUDA kernel, which you can look after the presentation. It makes use of the CUDA shared memory, and okay, that's it. Next slide. Okay, the conclusion. In our application, since we're doing this video processing, the convolution is really the main stuff. It's really heavily used. We have around 70 convolutions per each frame, and before optimization, it took about 60% of execution time. We optimized in a couple of steps. First, we used the simple kernels, which executed faster for smaller convolutions. We approximated large convolution with small ones. Again, we avoided misaligned memory access. Actually, that is one of tips from CUDA programming guide. And at the end, we used an efficient matrix transpose. Okay, that's it from me. And if you have some questions, you can make them now.
I see two hands here.
So can you give some sense of the amount of time you spent coding with CUDA versus on the i7?
On CPU. So Nemanja, the question is, what's the amount of time spent coding for a GPU, coding. That's a good term, coding. Coding for a GPU as opposed to the CPU. But I'll just get a remark that our development flow goes that after we done research and our first code implementation is on a CPU. So GPU implementation already has all the CPU code available, and some of the things obviously are figured out then. But Nemanja, I'll let you answer this question.
Okay, can you repeat the question, please?
Okay, the question is, what's the ratio of time spent like GPU development versus CPU development?
Okay, well, that is really hard to compare, because most of the time used for CPU development is actually used on research. So compared to that time, time needed for CUDA development is maybe 10 times less or more. So most of the algorithms can be done in one day.
Yeah. Okay,
because when actually my situation is when I get the algorithm, everything is known. So I know what I'm going to do, and the only problem is to optimize the thing. and that's it.
Yeah,
And,
here's another question coming, Nemanja. Stand by.
Okay.
Have you seen improvement in the newer hardware, maybe that helps with the misaligned memory access?
So the question is, have you seen improvement in newer hardware like G200 compared to G80 with respect to misaligned memory access problem?
Actually, actually, we didn't test that.
Okay.
So I know that the pattern for accessing and the rules are somewhat different, but I don't actually know how different. So we didn't test it. We wanted to make it as fast as possible on 8 series.
Okay, another question.
I was surprised that they're spending more time on convolution than on motion estimation.
That's because, I can answer that. That's because we use...
Repeat the question for
Would you mind repeating it?
I'm sorry.
Because there's some
Okay.
remote viewers.
So, Nemanja, the question is, why are we spending more time on convolution than on motion estimation?
Actually, convolution is really heavily used in motion estimation process.
My next question, are you doing the motion estimation?
Well, I can certainly answer that.
Question.
Oh, the question is, how are we doing motion estimation? So I probably don't have much time to talk about it, and also it's part of our proprietary algorithm. So I can tell you a little bit about our motion model. Obviously, it's not a matching problem like block matching. It relies on hierarchical gradient descent approach. We have various motion models, starting from global camera motion to parametrized a local motion where we can, down to an optical flow, but really all that plugs into the rest of the reconstruction problem and multi-frame reconstruction problem in a way that you can have mixture of models and feed it into the rest of the fusion filter of the fusion process.
And one quick follow-on question then. You showed improving jiggle from the camera. The examples I've seen of that have had to crop the scene somewhat.
Yes.
In order to capture the part shared by all the video. Are you recreating the missing part, or are you showing crops of both before and after?
Right now, in the software that's shipping, that you can go and download, you have a zoom slider. So yes, we are not doing any inpainting. It has black pixels on the side. Now, if you do a region of interest stabilization, then it's easier because you have known pixels the other side of the border. Now we have some ideas on how to do smart inpainting, but it's on the roadmap. Right now, it's just a slider where you can control the zoom level, basically crop level.
I have a question on the memory management.
Mhm.
Your main idea is to have a huge space, then you manage the memory by yourself, or you already have several pointers for different frames, then you use the pointer. Because I know for video, the frame size is perceived, you can always reuse the pointer. So is it your main idea to manage the memory?
So, Nemanja, the question is, are we using the same? You want to just repeat that again? Sorry.
Is it you have a very huge?
Mhm.
At the first time you allocate a very big space, then you will do the manual by yourself, or
No.
you already have several pointers for each frame, then you reuse the pointer.
So the question is, do we allocate all this memory space up front, or we have, and then have pointers to separate to individual parts of that memory, or we do it differently?
No, actually, it's some kind of lazy reallocation. So each pointer is allocated when needed, and this memory manager actually takes care not to deallocate it right away, but to reuse it somewhere else or in some other time. So the pointers are being reused. So if you are not running any processing, there is nothing allocated, and the pointers are allocated as needed. So if in one filter you allocate some size of memory, let's say I know at 1 megabyte, use it and then release it back to our memory manager. And in next filter, you are requiring the same size, which is very likely because you are processing the frame of the same size, the same frame. You are requiring again 1 megabyte of GPU memory, so the memory manager just returns the same pointer.
So I'll just add that some of the filters dynamically change size of the frame, so you can dynamically turn on your super resolution factor 2x and 3x, so you can run it 2x for 10 seconds and then go back to 3x or go to 1x. So we're going to be looking for the closest memory that we already have in the manager and try to allocate it. Same thing with this cropping or zooming problem of stabilization. So as you're moving this crop to get rid of the black bars on the side, you're going to need smaller frame to process. So you may reuse if there is something that's slightly larger than that, but if it's something smaller, then you need to, and there is nothing that approximates that memory size, you have to allocate again.
No, I think
Yeah.
we should do this. Yeah.
And Nemanja is going to stay on, and because we're over time, I just want to wrap up and then go with the questions, if that's okay.
That's great.
Nemanja, stay on the line.
Oh, okay.
Okay, so I'll go really briefly, this is my last slide, about the vision and where we hope to see this going. Right now, and I'm going to focus here on the consumer side, like the mass market, because we have our forensic line that's going to people who need it. And so this is our core engine. This is what you get. It's our core engine DLL that gets installed on your computer when you install vReveal. And vReveal is the application, our consumer application. Okay, so right now it's used to fix video that you have on your machine locally. But eventually, we certainly hope to build a framework and then build applications either ourselves or to allow other people to do it, to access our core processing engine, leveraging again GPU power from different applications like instant messaging applications, just like watching different internet video streams coming in online, or definitely plugging in with other people that are doing, because right now our decoding and encoding are on a CPU, so we would like to work with guys like Elemental. Definitely, we right now CUDA and NVIDIA. CUDA is what we work on. NVIDIA is our partner, but we are open to moving to new architectures. And what I've been talking about here today, I certainly see us making this framework start to end, from decoding and the memory manager and handling the workflow of multi-frames on the GPU and then getting it back more open and in some shape or form available to everyone, you included, where in that case you'll only need to write your own filter for whatever you want to come up with the best, or better stabilization, or some better auto color, or you just have a fancy filter that you want to try. You can simply plug it in and forget and don't worry about decoding and encoding and memory going up and down. You'll just get direct access to all the frames that are on the GPU. So that's what we're excited about. And I'm just, for you to get an idea, I'm gonna while Nemanja's Nemanja, you still there?
Yes.
Okay, good. So with that, let me just see if this is right. This is my last slide. So just want to thank the entire team at Motion DSP, starting from Sean Vera, our CEO, and especially my engineering team in Niš, Serbia. where all the magic happens. Ivan Vuchkovic, our lead developer there, Ivan Velichkovic, the lead researcher, Nemanja, who was with us today, and everybody else in Niš. Bravo, momci. Professor Milanfar from UC Santa Cruz, my advisor, Professor Janusz Konrad, who I worked with for 6 years at BU, and our current partners and in part investors, In-Q-Tel and NVIDIA. So that's it. Now we're open for questions, and
let's thank you definitely deserve something for trying to do a lot with technology and getting part of the way there. I guess we still have the demo to see, and we can do that afterwards. We can come down and see it. But before we wrap up, let's take a few more questions.
Maybe let me ask a very high-level question. So let's say if you get another 10 times speed out of the whatever, Laramie GPU, what are the additional things that you will be able to accomplish with that? Maybe repeat the question so that you know.
Sure. So Nemanja, I'll try to answer this question on from my side, and I'll also.
We have some remote viewers, and they are also like to hear your question.
Okay. Sure. So the question was, if we had 10x power, what would we do with it in terms of?
What if we had? I didn't hear.
If we had 10 times more processing power, following Moore's law, a couple of years down, we have 10 times more processing power than we have now. What would we do with it? And I'll answer that question from my side. Number one, you saw that right now we are about real time on state-of-the-art hardware doing VGA signal 1-to-1 using, I think, 7 matching frames, total of 7 frames. You can certainly see, people wanting to do SD to HD, which easily would take, maybe not all of 10x, but would take, probably 5x here. We see a lot of requests from surveillance applications where they would also like to monitor large sizes. Now, in terms of quality, we did our best, and in some places we did cut corners. Maybe instead of running more iterations for if you're gradient descent, or starting at a one more level of pyramid up, you would start at a suboptimal level because you wanted to get it where it's now, so your results might be better. And then definitely there are more things that we think we can do, especially in forensic scenario with objects, and maybe make use of an object that gets occluded but that's come back to the scene again, because that would assume that you can follow something along like a much larger buffer, but then having intelligence to combine those features. So maybe something's visible for 5 frames here, and then it's occluded for 50, and then shows up again, and figuring that out. So Nemanja, you want to take a shot at this question?
So I will only say more iterations. So for most of the algorithms, more iterations. That's it only. At quality, at concerning quality.
So in your conclusion, it seems like there could be a lot of value in using more frames for iteration, right?
Sure. Well, right now it depends on our forensic application. I'm going to try to bring a couple of clips in. In this application, right now you can see this is. I'm trying to populate my library here with the clips. So this is. I just want you to see how the application looks like. It has a user-friendly gallery from which you can kind of preview your clips, and then you go to enhance mode. And there are, nice big buttons for, clean and sharpen. Clean is basically this multi-frame processing. And if you go into, this is the famous one-click fix. And if you go into fine-tuning mode, then you can see, no, this machine is garbage. So you can see that here we have for clean, this is difference between 3, 5, and 7 matching frames. This is what we call, low, medium, and high. In our forensic application, depending on its version, it goes up to, 30 or 50, depending on the version. So we already have, in that application, many more frames now that's nowhere near real time. If you want to get real time with 50 frames, then you certainly need 10x. Did that answer your question? Okay. Oh, I'm sorry. You already asked the question. Yeah, let's do a full round.
I'm curious whether your forensic clients whether they expect you to prove rigorously that they can trust the output of your.
Right. So the question is, do our forensic clients trust us to preserve or like being able to verify what we're doing in our video processing chain? Was that a question? And the answer is yes, they do trust us because this is published. This is based on published and patented research. I think there I forgot what's the exact name of the law or regulation but I'll try to paraphrase it. If the technology used is published in a peer-reviewed journal, then it satisfies some of. I'm not claiming that that's the full requirement, but it certainly helps you getting into law enforcement, for example. Now we've had forensic labs using our software, winning court cases with it. And unfortunately, that's the part of the story that I'm not, very familiar with. But I can get that answer for you.
So if I could do a follow-up question, I think the question. So if you imagine you have this third part, which is AI, right? So you can imagine in the future when you've got 100x,
right.
You have a canonical human male model or set thereof, and you say, "Gee, I've got fuzzy video on this male in my forensics app. Let me make him look like the canonical model."
I see.
Right? And now it's pretty clear that that's the wrong thing to do in the forensics app. Right?
Absolutely.
So, I mean, how do you do any amount of verification to show that when you hone in on a license plate, you haven't somehow accidentally turned a 5 into a 4?
It's a very good question. So the question is there any amount of either intentional or unintentional tweaking of the algorithm that will make the result maybe look better, but look like something that's not really in the data? Well, all I can say is that we don't do it. But it's a very good question. I mean, at the end, it's the code that we've written, and if worst comes to worst, someone will have access to that code and see how things are running, line by line. Now, what's going to happen in 10 years or 15 years, and how that code's going to look like, and what level of AI is going to be involved there, and whether it's going to be fully deterministic as it is now. Because I can show that every run of software with the same parameter is going to produce exactly the same result. Whether that's going to be the case like 10 years from now, it's unknown. I really don't know what's going to happen there, but we don't do it. It wasn't me.
So let me ask a similar kind of question. Do I have to worry about somebody taking a YouTube clip of a credit card of mine and now being able to read the credit card?
Perhaps. It's we. Okay, so the question was, should we be worried about someone getting some of our personal information, like credit card number of video from our credit card, and fixing it? Now, number one, it's probably not smart thing to have any sort of video of your credit card on YouTube or any kind of photo in the first. In the first place. So it's a tool for tool that we provided to consumers and forensic community to go beyond what your eyes can see by really reconstructing all that data that is there, that's just spread around a number of frames. Whether it's going to be misused, maybe, probably. I don't know, but you know, that's the case with probably all technology that's built.
Maybe the last question.
Yeah, one last question. Here.
Well, it's continuing for a thread. From what I understand, your algorithm is not based on training data, right? It's based on filtered operation.
It's not based on training, no.
So then it is less likely to be guilty or biased, because any algorithm is going to be based on training data. It could be potential bias, like you do face recognition and all the people in the database have beards like Steve. The algorithm is more likely to be beard, right?
Right.
So here it seems like you are a little bit more agnostic when it comes to your code. So there's a chance on the board in terms of showing black and white.
The answer is yes, just to repeat the question. The question is because we are fully deterministic. We don't use any kind of training model to teach our algorithm what to look for, to look with people with beard or with blonde hair, and that we are less likely to be charged guilty of trying to tampering or at least having a bias. In the reconstruction? And the answer is yes, basically. We are planning, and that's a request from the customer, to introduce a special, right now, even when you're reconstructing license plates, we are treating that the same way as pixels coming from the baby or the dog or whatever. So we don't have a special license plate recognition mode, which certainly we plan to do. It's a request from the customer where you use some prior knowledge of the data you're trying to recover. It's uniform white or yellow background. It's uniform black or blue letters, and you only have a limited alphabet. It's whatever digits and letters, and then maybe you can use that to steer. So what we do is entirely in pixel domain. We don't care. We don't know what it is. Basically. Okay.
Fantastic. You have kept the audience here quite long, and they seem still engaged. So
okay. Thank you very much. Thank you.